Hey class, today we're going to start section 4 and we're going to split it into two sections. This section is about entropy changes in a chemical reaction if you are given one. And we're going to split it into two parts, learning about the system or just the reaction itself. And then part 2 is going to be about the surroundings. So as an introduction, in previous chapters, the last chapter we covered, we learned that calorimetry is a type of scientific measurement that we can do to measure the delta H values of chemical reactions. No comparable method exists to help calculate delta S values for a reaction, or basically the entropy. However, because of the third law of thermodynamics establishes a 0 point for entropy, we can use experimental measurements to determine the absolute value of entropy, or denoted by the letter S. What we do is we look at the entropy of a substance and comparing it to temperature. So since we're talking about this third law and how we've used the third law to come up with standard entropy values, let's kind of review what the third law of thermodynamics is. Basically, it states the entropy of a pure crystalline substance at absolute zero, which is 0 Kelvin, so let's just reiterate that, 0 Kelvin is 0. And we know that entropy is going to increase as the temperature is increased. Now, entropy of a solid is going to increase steadily the more temperature you put into it until it reaches the melting point. And when the solid melts, what happens is those atoms that were tightly bound together in a crystalline solid are free to move around the entire volume of space that they're given, whether it be a bowl, a cup, a room, a flask. This added freedom of movement actually increases the randomness that we learned in the last section and therefore increases entropy. In fact, when we see things undergo the melting point or undergo melting, we see a very sharp increase in entropy. This is denoted by this picture here. Here we're at 0, and as we increase temperature, of course, you're going to notice entropy is increasing as well. When we get the melting point between a solid and a liquid, notice that there is a sharp jump up. Here we're going to talk about on the next slide how even after it's melted, entropy is going to keep increasing with increasing temperature until it gets to between a liquid and a gas. During the boiling point, there's going to be a sharp increase in entropy again, and then the temperature is going to keep increasing. So just like we said in the last slide with the picture, I said we were going to talk about it. Entropy of a substance increases even after it has melted, and it keeps increasing until it reaches that boiling point. At that boiling point, there is another jump in entropy, and this is because there is even more freedom of movement when things turn into a gas. And remember, gases move about very quickly and very randomly. And even after it's been a gas, you can still heat it and entropy can still increase as well. So again, it brings back that picture. So another change that occurs at high temperatures is that the distribution of the molecular speeds increase. With more temperature, there are higher speeds, there's more kinetic energy, and there's more disorder, more randomness, in other words, or entropy. So entropy generally increases with increasing temperature. Again, because there is more thermal motion, means there's more possible microstates that can happen. So calculating entropy. What we just saw on the last slide, well, 2 slides ago, with the chart with melting and vaporization, those are called entropy plots, and they can be obtained by carefully measuring how heat capacity of a substance varies with temperature. And what we do is we use that data to make a complete data sheet of absolute entropies at different temperatures. So entropies are usually tabulated as molar quantities because molar is our SI unit for the amount of a substance. And so therefore, usually entropies, when we find the delta S value, are going to be given as joules per mole Kelvin instead of joules per Kelvin. Now, molar entropies, if they are in their standard states, remember standard state is anything that is in a pure substance at 1 atm at 298. So if it's a solid at room temperature, that's what it is. Those are going to be standard molar Entropy is denoted by S with a little circle degree sign. Now, standard molar entropies, we're going to talk about what they are. We're going to talk about common themes we find within the numbers, and we're going to talk about how it's different than enthalpies of formation that we did in the last section or last chapter. So enthalpies of formation, which are delta H values, there is a big difference. Standard molar entropies, if they're in elemental form, they are not 0. So for example, during the delta H enthalpies of formation, if you had oxygen gas, that always had the value of 0, and we're not going to see that in this case. Part 2, it says the standard molar entropies of gases are higher than liquids and solids. That makes sense. There's more randomness in a gas than in a solid. And then it's part 3, says standard molar entropies increase with increasing molar mass. And then part 4, standard molar entropies increase with the increasing number of atoms, or basically the complexity of a formula. So here we have the standard molar entropies that are given within the textbook that I use. Notice that the hydrogen gas, nitrogen gas, oxygen, lithium, sodium, potassium, iron, their values are not 0. They actually have values that you have to look at. Notice we're using S values instead of H this time, and notice the unit up here. Another thing I want you to notice is how even states of matter still matter. So here we have a liquid, and here we have a gas. The gas has higher entropy. And even if we go even more complex than that, let's hide this from you. We have FeCl3, about 142, where you have a lone Fe, which is 27. Notice the complexity or number of atoms increased, so did the entropy. So in general, we just stated in the last slide as part 4, the more complex a molecule is, the more entropies they're going to have. And the reason for that is because generally the more atoms you have, you increase the number of freedoms or degree of freedoms, the amount of atoms they're able to rotate around. So again, that increases those microstates again. So how do we calculate entropy change for reactions? Well, entropy changes for a reaction is estimated the same way or calculated the same way as delta H values that we did in the last chapter. Here we have delta S, which is the change in entropy, is going to be equal to the sum. So remember, this equals the sum, sigma. You add of your products minus the sum of your reactants. So it's always products minus reactants. The value in, again, are the coefficients from a balanced chemical equation, and M over here as well. These delta S values are going to be given to you in the same handout that I gave you for delta H values, and it can be found on my class website. Here we're extra example. So here we're going to do an example of calculating the change in standard entropy of a system for the synthesis of ammonia from nitrogen gas and hydrogen gas at 298 Kelvin. Okay. So here what we're going to do is we have to do products minus reactants. So these comes first, and here comes second. So again, here we have 2 times my number I have for NH3 as a gas, and NH3 as a gas is going to be 192.5 minus, so products minus, here we're going to have reactants, so 1 times whatever nitrogen gas is, which nitrogen gas is going to be 191, plus 3, because there's 3 hydrogen, times hydrogen gas, which is going to be 130.6. And then we have to go ahead and calculate this. If I calculate this is 385 minus 191.5 plus 391.8. And when you go ahead, you got 385 minus 583.3. And this comes out to be negative 198.3 I have to have a unit, and up here, remember delta S is going to be joules per mole Kelvin. So if I look at this number, since we're talking about entropy, this is a negative. So that means this is going to be less entropy, and we're going to become more orderly, or in other words, less random. Here I have a problem for you guys to try. Let me know if you have any questions, and pause this video and go ahead and try it. Okay, so if you were going to try this problem, again, remember products minus reactants. Here you have your product. Water is going to be first. We're here, these are going to be second. So I have 2 water. Notice I have liquid water here. Pay attention to the states of matter. So if I have liquid water, it's going to be 69.9 minus, here I have 1 oxygen gas, so oxygen is going to be 205.0 plus, I have 2 hydrogen, so 2 times hydrogen is 130.6. And then you can go ahead and solve. When you multiply that, 139.8 minus, we still have our 205 here, but when you multiply these two values, you get 261.2. So we get 139.8, and when we add those two values, we subtract it, 466.2. And this gets us negative 326.4. Again, we're going to have a unit. So if we look up here, it's going to be joules per mole times Kelvin. Once again, we have a negative value. This means we're going to be more orderly, or in other words, less random. So that's the end of today's lesson. Let me know if you have any questions, and I'll be more than happy to help. And I hope you guys have a good day.